Okay, everyone. Is this one loud enough? Cool. So today we get to the second lecture, but before we start, I hope you still remember what I mentioned about SLAM last lecture. So today we got a SLAM people here, and he will be talking about how you can access to SLAM in the following weeks. So let's welcome, please.
Thank you. Good evening, everyone. So my name is Ben, and I'm a mentor from SLAM. And I'm here to talk to you guys that SLAM here to support your studying in this semester. I'm here today because your course is one of the courses that SLAM supporting in this semester, which means that in SLAM we have mentors who are also students, just like you guys here. But the difference is that they all have finished the course. This course, particular course, and they all got D or HD out of that, which means they are good students, doesn't it? And here, I got a piece of information. I'm going to leave it here, so you guys can contact SLAM anytime during the week. SLAM going to be open from next week to the end of the semester, which is week 12. Even though it starts from next week, but if any one of you guys come to SLAM this week, you're gonna have a chance to win $100 vouchers. Otherwise, if anyone who's are not lucky enough, you guys still have free donut. So please come to SLAM because we are students just like you, and we understand how challenging the course is gonna be. Obviously, we also a student and we find difficult. We highly recommend you guys come to lectures, or highly recommend you guys come to a tutor first. But if you want to hear a different perspective of that difficulty from guys that actually get the same difficult just like you guys, then please come to SLAM. Don't be scared, don't be nervous, don't be afraid, because we are all students, isn't it? So thank you guys very much. We are located in building 8, level 7, and we have 3 rooms, which is 151, 153, and 48. So they are spacefuls. Welcome to bring your friends or your group with you if you guys stuck at the same spot. Please, just come. It's going to be so fun. I'm serious. Thank you.
Thank you. So let's get to the donut. Okay, now before we start, I do need to mention one thing very important. So I do need to apologize to you guys because in the first lecture I forgot one important thing. So let me bring for you. Okay, let me make it clear. I do understand, as I mentioned in the last lecture, this course is a bit different from the other courses. So it involves math, coding, algorithm, so it's quite a lot. I do understand it is different, and possibly you can translate it into something called difficult, but it's different. Okay, so I understand. So what I try to do is, as long as you can answer a good question or give me a good question, you get chocolate. So today we start from here. Okay, now let's go to the second lecture. I hope it helps. Okay, now, we first go to the overview. So within the overview, don't be scared. I did not plan to go through everything covered within the list. I hope we can get up to 0.5. So that's the aim we try to get today. So let's say. So we first go to the overview and then the fundamentals. So I would say choosing to attend to the lecture is really wise because today's lecture will actually cover all those most important concepts in this course in the following weeks. So the concepts are actually quite abstract in nature, so I do understand. So so bear in mind I know even for me, the first time I saw all those concepts, I was a little bit overwhelmed as well. So don't worry, if you do understand, that's great. So if you don't understand after the lecture, That's fine. Go back home, watch the recording again, and then attend the tutorials and practice and try to make it understood. So as I mentioned in last week's lecture, so there are two tools actually for those math foundations for this course, and the next with the tutor will be one of them. Another one is actually put in week 6. So that will be those two tools. Make sure you attend the tools as well. So now we are good to go. Okay, first we get the overview. So before we go to the AA, we call algorithm analysis, I always want to encourage you guys to say, why we need to do that? So basically, why we need to compare the complexity of algorithms. And for what reason? Be able to do that, what do we need to do? So we get several bulletin points here. So we need to be able to measure the complexity of the algorithm. And then we should be able to compare the complexity between algorithms. So we measure first, and then we compare. And then, as an example, we'll work on the two very popular, or the two actually big popular algorithms, recursive and non-recursive. And finally, we go to the empirical analysis. So that term will not be covered in this week, but I do want to bring your attention something like theory is what we're talking about, the theory analysis of the algorithms, and the practice will be something like we call empirical analysis. We cover that later. And now we start from here. Okay, now we get one example. Assume you graduate, or even you did not graduate, but you get a job because they are so good. So you get a job within the medical stock. It's highly possible because I talked to one of you today in the corridor, and he got some kind of job within ANZ. That's brilliant. I like it. So it's highly possible you will be one guy be hired within the medical stock. And you are the only guy expert within computer science. So your boss come to you and ask, right now we get one problem. So the problem is we get all those medicines unsorted somewhere. And our employer needs to go search for some of the medicines. And here I get two options. Can you tell me which one is better, faster? Now here I get the two options. Option A is the sequential search. Option B is the sort and search. So basically sequential search is you get 1,000 of the medicines. You search by comparing one by one. The second one will be, okay, I will sort all those medicine in alphabet order or in order of the prices. Whatever it is, you sort first and then search. Can you tell me which one is better? Do not yet out. Try this form. Get out your phone, scan this QR code, and fill in the answer. Okay, now I get 25 responses, but it seems I get more than 25 people in the classroom. So please take out your phone and scan this code and fill in that form, please. Feel free to discuss with the people around you. So all the slides are actually in the Blackboard. If you get a laptop with you, you can download the version from there and scan from there, maybe easier. Cool. Let's go back to check the responses. Wow, great. So don't care about those the percentages. I can tell you right now, at the moment, both of those algorithms are equally good. So there's no right or wrong answer. So what I want to get from here is some discussions, and then I will show you some insights. Okay, cool. Right now, who select the solution A for sequential search and give a possible explanation, please? Please. Sorry. Great answer. I will try. I'm sorry if I hate anybody. Perfect. Okay, now the answer is actually correct. So can any people actually give the answer for if you select for the second solution, sort then search?
Would you sort the medicines into categories, and the person looking for the medicine knows the type of medicine they're looking for, they can just go to that category and then the search, like the total number of medicines to search amongst is less. It's ultimately quicker than doing a sequential search throughout the entire one.
Okay, cool. Good solution, good explanation. So I will try. Sorry. Okay, now do you mind who answered the first question? Do you mind I ask you, okay, what if we perform the search for many, many times?
If you're doing lots of searches, then sorting the list once and storing the sorted list would potentially make it faster if you have a means of going directly to the right category.
Yeah, excellent. So that's what I want. Okay, now I will summarize. So one thing. So could you please guys keep silent before when I was talking or the students are talking, because if you're talking, the other student cannot hear. Okay, now I will summarize. Excellent solution. So there's no right or wrong answer. I said at the moment, both of these methods are equally good. The reason is I want to get two things from here. The first one is there's no one good solution to suit all those contexts, because the question really highly depends on different contexts. If you only need to search one or two times, sorting thousands of those medicines may take more time. But if you do need to search for everyday basis, so I think sort and then search would be better. So as you can see, it really depends on your problem. So that's the first one I want you get from here. That's why we need to answer something like, we do need to understand some of the algorithms and the analysis. Second one is, I hope you can understand, by asking these questions, you were thinking something like, which algorithm is better? In terms of what? In terms of what? How many times you can get the result? How quickly you can get the result? So that's it. And for today's job is we give this one answered, and we need to measure. We need to measure at a very precise way, but at the same time it's actually on the theoretical level. So now let's proceed. Okay. So we get this thing, three things we put in here. We estimate the running time of the program, and we also need to compare the running time of two programs. The point here is we want to do that without we implement it, without deploying that algorithm. Because sometimes some of the algorithms really will run for ages, you don't really want to do it. So what we prefer is, before we really do anything, before we take any action, we want to do some analysis on papers first. So that is the power for AA for this course. Now we get down here and we say something like this. Two terms, space and time. And possibly some of you heard something like time complexity and space complexity. And then in this course, we will focus on time. the time complexity. That does not mean space complexity is not important. That only because we only get 12 weeks. So we cannot cover everything. So we focus on time complexity, talking the complexity of the algorithms. So that will be the point. Now we go to the fundamentals. So when we go to the fundamentals, we get the first question. How do we estimate the running time of algorithms? So the idea will be something like that. The fact is the algorithm does include some kind of those operations. When you want to use that algorithm to get a problem done, you need to run some of the operations in there for a certain number of times. So that operation and that number of times to run that operation is the point we try to capture. And here we get something special for them. So what do we call them as the basic operations, or we call the number of times we run is actually depends on the size of the problem. So two concepts, the basic operation and the size, the input size of the problem. And the input size of the problem actually will affect the number of the time you need to run that basic operation. As long as you put all these concepts run out together, great. Now, to make our lecture a bit solid, I get a running example. This running example will be used throughout this lecture to help us to get all those concepts. Now we get here. So the example is actually to calculate the a to the power of n. Just in case you don't know what actually is a to the power of n. So the basically means you get a, you multiply a again until n times. So you get a to the power of n. So now we get a very nice and short pseudocode. This pseudocode is actually doing the calculation for the a to the power of n. Now we get it from here. So we are going to show each line of them. So we get two inputs, a and n. A is the base, n is the power, and we get output is the calculation. We get 5 steps. The first one is we set up S initially as 1, and then we get a for loop. So as long as we get a for loop, you may think, okay, for loop is something you actually loop through something and do a number of times. So that one is we get the loop index I, start from 1 until n, and then we do something like this. We do the calculation of S multiply A, and then assign the value back to S, and we do it again until we find, okay, I is not less or equal to n, then we stop, and then we return S, the final value. So that is the way we do. Okay, now we get this one simple, so we get to understand. So the next question is, can you identify the operations in here? Okay, so you're actually quite quick. So now the question is, we want to get the basic operation, but before we go to the basic operation, we need to discuss all the operations like this. So in line 1, we get assign. In line 2, we get possibly something like we assign value at the same, we compare. And in line 3, we get multiply, and then assign, and then we return, we end, we return. That's the operations. And from here, we get a lot of different operations, but how do we define which one is the basic operation? So we get different operations, we find which one is the basic one. Okay, now we get several terms here. So first we want to say, okay, the basic operation is the one we want to find that one contribute most towards the total running time of the algorithm. That's the first item we need to notice. We get examples like all those kind of combination. So all those kind of operation can be a basic operation. You add, multiply, print, compare, divide, or something. And then the operation is also the one you most frequently executed in that algorithm. So now we go back to here. So can you tell me what are the basic operations of our example algorithm like this one? So can you tell which one it is, or you get a different explanation?
The comparison and multiplication are the basic operations.
Okay, very complete solution. Great. Cool. So now, At the moment, I would tell you, okay, all the answer is correct. So you get a sum, you get a compare, you get a multiply, all correct. But later, as we proceed to the following around 10 slides, you will find we will focus on one of them. Like here, I would say we'll focus on multiply. Because comparing to a sum and compare, multiply is the one possibly taking more time. It's more complex. So we ignore the other ones. So we call that one is dominant at the moment. So we call, at the moment you can say, oh, that's a sum, compare, or multiply, all correct. Okay, now second question. So what is the input size? So remember right now we're talking the size of the problem. We're talking the size of the problem. We're not talking a specific number. So for example, we want to do a search across an array length of n. So the input size n is actually is the input size. But if we go to something like this, we want to know what we really want to do here is actually we want to use the input size to find the number of times we need to execute to solve that problem in this algorithm. That's it. Now, let's go back to our friend. So n to the power of n. And within here, can you tell me what is the input size? Note, here we get two input. We get a or we get n. Guess which one is the input size? Oh my God, you are genius. Can you tell me why? Let's keep one people talking. Okay, cool. I think that's a good answer. Sorry. Okay, now, I do agree with you, but let me clarify something a little bit more. So while we see this one as the input size, let's do something like this one. Easy calculation. Let's assign a equal to 2, n equal to 3, and then we change a to 3, and n is still 3. So initially we calculate 2 multiply 2 multiply 2 3 times, so we get the result. And when we change a to 3, we 3 multiply 3 multiply 3 times, we get the result. We do 3 times the calculation. Yes, there are differences between you calculate the 2 and 3. But is that difference so big? We don't know. So we compare, what if we keep a the same and we change n? A is still 2, n is 3, and now we change n to 4. Initially we do a multiply a, we get 3 times. And now we need to do a, we get 4 times. You do one more round of calculation. So from here we can say, okay, as long as you can increase n, you do change the size of the problem you try to solve. So in that case, we would say, okay, n and a, when you change them, they both have impact on the complexity of the calculation. But the n dominant, that change. So we say n is the input size. Now, we get something to call. So basically I get the 2 chocolate here. Now let's try the first one. First one we get a case is something like this. We get a real size of n. I will try to print each of the content. So can you we get the input size, as we said, the size of n of the array. So n is the input size. Can you tell me what is the basic operation? Sorry, who was? Okay. Increment across different of those elements within the array. Okay, cool. That can be one solution. Any more solutions? Let me try. Sorry. Okay. Any other solutions? You get a second one. Yeah, correct. So why here I will explain. So either you do the iterations through each of the atom, that's correct. That's a basic one. But remember, we get something like this. Sorry. So we get something like this. Printing itself is actually quite expensive. Printing it is expensive. So comparing to printing, we tend to ignore the other factors. So we call printing will be the basic operation in this case. Now we'll go to the second case. Second case is something like this. We get a number of n points in the 2D space. What we try to do is we try to find, you go through all those possible pairs of those points and give me the closest pair. So can you tell me what is the input size? Because I write down the basic operation is to do the comparison. So what is the input size? Say it again. Okay, my God. And other solutions? Okay. Okay. Any other solution? And what? Okay. This one? Okay, n factorial. Kind of right. Okay, let me explain what I mean. It is something like that. So within here, what we do is actually we do something like this. We give n point, and to find the nearest, to find the closest pair, you do need to compare between each of the possible pairs. So you may have n multiply n minus 1, kind of a comparison like this. And if you calculate that, that's good. That's the time of the comparison you need to do. But what are we talking here is we're talking about the input size. And we get the concept of input size first, and then we're talking how the input size dominate the number of time you run the basic operation to solve the problem. So there are different solutions. So the right answer is n. The right answer is n. So I think I need to give several because I do want to get some discussion from here. I remember 3 of you actually, right? I think you get one. You get another one. I'll try to make it. Come on. Great. Okay, now let's continue. Okay, so we'll get another question. So please keep quiet. So after we get the basic operation and the input size, how do we use them to estimate the running time of the algorithm? Warning, here we'll get something called mathematics. But before we get the real math equation, I get some of the text first. So let's read it. So the running time approximately equal to the time to execute a basic operation multiply the basic operations. So if we put this one into a math, you can see it's basically the same thing. We just use different terms. We use different terms to note something. For example, we use Tn. With Tn, we call this one the function. T means that's the time for running this algorithm. And n actually is the input size, so it's in the brackets. And we use this one, say that's approximate. And the COP here actually is the C underscore OP. It's the execution time for a basic operation. So execution time for a basic operation. And the point here is the C, big C and n. So we can say the big C n is actually is the number of times we run the basic operation. And the input for this is n, is the input size. So from here, what we can say, for the definition for Cn, for define the number of the number of times running the basic operation, it is actually a function of your input size. So let's bear this one in mind. We'll look at that later. So what does this one mean? Okay, now let's meet our old friend again. So that's the one pseudocode to calculate for the n to the power of n, and we want to get the theoretical time running for our algorithm. So we record the equation is something like this: Tn approximate to C underscore OP multiply Cn. So the question right now is, we do need to know something like the basic operation and the input size. For basic operation, I think we get it already. So as I mentioned before, you get some values. you get a multiply, you get a comparison, but we choose to use a multiply as the basic operation. So we know the basic operation already. So the basic operation actually mean this one. So the basic operation will actually contribute to the running time for that basic operation. And say capital Cn is the one actually control how many times you need to run that basic operation. Okay, now what is Cn, big Cn in this case? Yeah. So because Cn equal to n is we get a loop here, we need to do this one a number of times. It's actually controlled by from 1 to n. So that's it. So now we get something like this. Now you can say the math in AA is not that difficult, right? It's something we say, we just count numbers. Now we go to the point. We will use capital Cn to count how many times you need to run that basic operation to solve a certain problem. So that's the whole story. Okay, now we put everything together, we will get Tn finally equal to the basic operation of Cp, the running time, multiply n in the size of the number of times to run the basic operation. So now, let me tell you at the moment. So I will keep talking all those important concepts. For example, like the capital Cn. So the number of times to run the basic operation. I will not talk too much about this one. I will not talk too much about the time you run for each of the operation. The reason is something like this. Because that one really depends on your implementation. Different algorithms, different softwares, different hardwares. And later when we do those theoretical analysis, we actually will drop this one. And we treat it as a constant. So we drop it, we will focus on the following Cn. So now we start the next one. Let's get one more example. One more example is we get a sequential search. Remember, your boss in the medical stock asked the first question is, how actually is the complexity of a sequential search, or your sort and search? And we consider sort and search later, and here we focus on the sequential search. Now we get a sequential search like this. Remember now, for the sequential search, actually we give input like one array and one value, k. What we want to do is we want to find whether k is in the array or not. If it is in, tell me where it is. Now let's look at this example. We got a sequential search. And one thing more I want to mention here actually is, you possibly noticed what actually will represent this array is actually something like the real array implementation when we're talking about algorithms. It's not a linked list. So we can access by those indexes 0, 1, 2, 3, 4, 5, 6. So that's the one we quickly access to each of those cells, and now we can do something later. So now we try to do something, we do something like this. So that's what we can access for each of those items by using these indexes. So you do not need to use a linked list, go through some of them, find the final value. I hope you can still see the connection between lecture and your practice. So make sure you attend the practice. The practice is really important. So I hope you can see it. Now let's go back to this example. So this example, we start from here. We get an input, sequential search, we get 5 steps. We initially set up I equal to 0, and we get a while loop. And we loop through all those elements within A. And for each of the element A, if it is not equal to the value we are looking for, and then we actually go to the next one. And then that's what we do. We end and we return. Okay, now I get a question. Can you tell me what is the basic operation in this case? Say it again. This one? This one? Correct. So any people get other answers? Cool. Thank you. The comparison? Yes, also correct. So within this case, we get a different concept. Like we can compare, we can use I, we can use add, or we compare, and we here is also a comparison. But for the operations of here, I see all these ones are correct. So you get another chocolate. Okay, now let me continue. So we get a basic operations like this. And for the input size, okay, any other options? Can you tell me why?
Like we are comparing from I less than equal to n to I n is the total size of this.
Great. Okay, now that's great answer. What I would say is, can you pay more attention to the next question? Thank you. Okay, now we know the basic operations and we know the input size. Can we now consider what would be Cn? I hope you still remember what is Cn. Cn, the number of times you run that basic operation. So can you think in this sequential search, what is Cn? The number of times the basic operation will be executed to solve that problem. Okay, I get so many answers. Can we do one by one? Okay, one solution. Yeah.
Because when we get the K, when we find the K, we start the so it can be from 0 to n, and maybe it is variable. It is variable from 0 to n.
Okay, kind of right. You get an answer?
I think my answer would be pretty similar here, that whatever the index position key is, because the while loop stops as soon as you get there.
Yeah, so the one in the back. Sorry.
Is just the potential, like the length of the array is the greatest amount of possible iterations that we require. Therefore, it's the length of A.
Okay, cool. Cool. So the one before?
I guess it will be n minus 1 will be the kth element. So
Okay. All good try, but not accurate. So let me show you what's the real answer. So, but I really, to get those solutions, discussions, so all your questions may be right or may be wrong. I will tell you why. The reason it depends on something like this. You get a worst case, best case, or average case. So something like it really depends on the K is actually in that array or not. If it is in where it is the first element you compare, then you get the best case. The last case is, well, the worst case will be, okay, you compare to the last, you found it, or you did not find it. That's all the worst case. If actually that K is in the middle of those arrays, and you get average case. So we get different cases. So that will be the solution. We get worst case, best case, average cases. Okay, now let me emphasize something like that. So when we're talking about the worst case, actually the maximum running time for any process, a possible input. The best case is the minimum running time for any process possible input. The average case actually is the average running time across all possible inputs. It's not the average of the worst case and the best case. Now let me repeat. So average is average across all possible input. Average is not the average of the best and the worst case. So that's the way we do average. In the following, you get one question? Okay. So in the following slides, I'm going to show you something to get the best case and the worst case. So for the best case, it will be okay, something like this. Whenever we find actually for this sequential search, we always find the atom being searched is actually in the first atom. So whenever we do actually is we just we just search once and then we stop. Search once, then we stop. So in that case, let's pay attention to what actually is say. So remember the big Cn is very important. So we need to pay attention to what is the big Cn for different cases. Best case, worst case, average case. Now for best case, Cn is always equal to 1. Because you need to do one comparison only, the first atom. The worst case will be, okay, the atom actually is not present in the list, so you need to compare with all those atoms, so you compare n times. So you get n times. So C, worst case, n is equal to n. Now, we get best case, worst case. Unfortunately, for average case, it's not that straightforward. So in the following calculation analysis, please just bear in mind what I show you is something like analysis for teaching for this algorithm. We do not expect you to do the average case analysis for a new algorithm. That's another story. So now we start. So we get something like that. Before we do the average case analysis, we need to get some other questions. The questions will be, how often do we search one item that actually is in the list? And how often you search one item that actually not in the list? If you search the item you try to search is in the list, where it is, first position, second, third, all that question we need to answer, or we need something we call assumptions. So when we do the average case analysis for this synchronous search algorithm, we do something like that. We will set up one of those things called a probability. We will set up one variable called the probability to control how is the probability you will search one item in the list and how is not in the list. The sum of them will be equal to 1. And the second, we will say, if that atom is in the list, where it is, first, second, third, I don't know. So I tend to be equal. So I would say, okay, equally, they may be in the second, third, or all those possible elements. So if you get the length of 3, and the transfer in 1, 2, 3 will be 1 over 3. So that will be the one we assume. So after we got this, we get a very big equation here. But I skipped some of the steps. So I will not do the calculation steps in the middle to see how do we do it. I will show you the result here. If you really want to know, I will upload it to Blackboard so you can have a look to see how do we get this equation from the assumption I just described. So now we get average case is something like this one. And here is P is actually the probability of a successful search, so which means whether the atom you search is in the list or not. So we can say P 1 minus P. So we get 2 terms basically within this average case say. The first case actually is for if P means you find the K in that array, you get the first term. The second one is if it's not in there, and you go to the second term. Here is the explanation. So if P equal to 0, which means that K is not actually in the array. So remember, we need to search for everything. So that's the worst case. So in this case, the C average is actually equal to N. And then if P equal to 1, and then we get C average N is actually N plus 1 over 2. So basically it means you need to search at least half of the array so you can find that atom. So it is reasonable because what we assume actually here is we assume the chance you will search the K value in each of the positions in that array is equal. So you need to go through half of it and then you can find it. So that's average. So that's the average case analysis. Any questions so far? Okay, great. So now, what do we cover? You get a question? No. So I got you. So the question is, if you have a specific value to search, possibly the one you search the time you spend to search, for example, you get, correct me if you get me wrong. So if you get an array actually equal to 10, size equal to 10, and the item you want to search actually is sitting in a nice position, and then the time you search for A in that case will not equal to this one, it is absolutely correct. Because what are you talking actually is an individual case for that. That's what we don't want to do. What we want to do is we're talking something theoretically on average. You search one item possibly sitting in the position 9, but if you search 1 million, so you will get a distribution around somewhere. So the distribution will mainly follow a normal distribution. So the average time will be the mean value. So actually is this value. So that's it. But good question. I'll give you a chocolate. Thank you. Okay, now any more questions? Okay, now then we will continue. So summarization for this part is we get the input size, we get the basic operation, and we use the input size or basic operation to analyze the complexity. Or we estimate. So we estimate. We do not do very precise calculation. So we estimate. And we get different cases because not all those algorithms have a very fixed operation you can run to get the solution. Most of the case is you will get the best case, worst case, average case. So for an algorithm, at least you need to understand what would be the best case, what would be the worst case. For the average case, as long as you can understand, that's fine. You don't need to really do the analysis because I understand that one is pretty hard. So don't worry. Yeah. Getting. So now let's continue. So now we go to something like a little bit theoretical. We call symptotic complexity analysis. So now let's start from here. So what we get is right now we have a way to analyze the running times. So we use the input size. We use the basic operations. We use the number of time you run that basic operation. So you can estimate the running time. But what if you get a running time that we still want to compare something? But the point here is each of the algorithms have their own time complexity. Then how do we compare? Because they are very different. Now let me give you some solutions. The solution is something like that. As long as they are different, we tend to use the idea of a group or grouping something. We group them into different things we call equivalence class. So from here, what we mean is all that algorithm and their complexity go to the same equivalence class. We saw they are theoretically they are the same. So now we get a concept called equivalence class. So that's the one we need to make it clear. Now start from here. Okay. I know that this one is a pretty abstract concept. So don't worry. We get one example for you, something like this. Now, I get two algorithms and their running time. You're still with me. The running time here we mean is the T. T1, T2. T1 for algorithm 1, T2 for algorithm 2. So we get the T1 equal to 5.1n, T2 equal to 5.2n. And on the right side, I actually get the plot out of those two algorithms in terms of n. The x-axis is n, the y-axis actually is the running time. And there are two lines. I think the red line actually is for the first algorithm. The green one is for the second algorithm. And here we get different values. Because what we say here is actually, if we assume n equal to 1,000, so if n equal to 1,000 and the T2's value will be equal to 5,200, so it's a bit lower. The red line will be a bit lower than the green one. So the green one actually is actually for T2. So we get those two. But now I get a question something like that. So are they similar? Because there are some differences. Do you think they get a similar timing profiles as n grow? Okay, can you explain why? Sorry. Okay, cool. Right answer? That's correct. The linear is the keywords. Is the keywords here. Great. No, so now we get this one. Now, if it's not that clear, so we do not mention linear at the moment. We mention something else. I'll give you another two examples. Another two examples is that the algorithm 3 and algorithm 4, so we get a T3, T4. T3 is 5.1 n squared, and T4 is 5.2 n squared. And then we compare those two, you will find something like this. The red is for the T3, and the green is for T4. Sorry. Yeah, that's correct. So now we get these two, we compare, we find they are also similar because the trend is similar. Is that correct? So the trend within T3 and T4 are similar, and the trend between T1 and T2 are similar. So if we really want to see the trend, we get a term like linear, quadratic, factorial, exponential. Later we talk. Right now we only notice whether the trend are the same or not. So right now we can see they are clear the same. Now, let's do one more thing before we continue. Can you compare the lines within this figure, upper figure, to the line in the down here? Are they got a similar trend? No, because this one goes something like linearly go up like this, and this one goes something like this. If we use a very specific value, we can make it very clear. Let's try 1000 again. We compare the algorithm T1 and T3, because they get 5.1 n and 5.1 n squared. So 1000, so we get T1 equal to 4100, and if we get T3, the value will be 5 million, 5.1 million. So which means they are very different, right? So the trend are very different. So we measure the trend. Okay, now we continue. So before we continue, I'll give another warning because some of the math definitions are coming. Something like this. The idea is before we actually group something, we will use some ideas. The idea here is actually called bonds. The bonds is something like this. That's the definition. Don't worry, let me explain with a picture. That will be easier to understand. Okay, now assume we get Tn. Remember what is the Tn? Tn is the running time for one algorithm, so we get Tn. So for running time, we get for Tn, and then we run it, we get Tn. And right now, what we say, we get an upper bound for something like this. The upper bound is really something like, if you get Tn like a line, and the Cgn is actually the upper bound of this running time, it's always above the Tn line. So visually, we can say that's the upper bound. Now we try to map it to the mass definition. So within the mass definition, for the upper bound, we get two terms. The first one is called C, second one is the Gn. C here actually, C is pretty magic here. So because we said, okay, C actually is a positive number, and the C multiply Gn can be a function that is an upper bound on Tn for some C, as long as C is positive, for some large n's. So you can see we get a dashed line here. We call it n0, and we put something like it don't matter. Sorry, does not matter. I don't care. What that means is I only care the large n numbers. So for n is large, as long as n is large, as long as you get one magic C number, and use the magic C number to multiply a function Gn, it's always upper. This Tn, I will call that one as upper bound function. So that's it. Any questions about this one? Okay, G is basically a function. G is a function. So G just like T. So the function will be T and a letter plus a square. So T is a function for the running time and N is the input space. And G is also another function, it's the upper bound function, and N is also the input space. So that's the Gn. But so for exactly what actually is the Gn, don't worry, we will use our old friend a to the power of n to do one example. Now, as long as we understand, for the upper bound is something like one function is always upper, is actually keep above the line of the current running time, and for the number when n equal to large, and then you get the upper bound concept. It's a bit abstract, but the meaning is something like that. Okay, now, after we get this one, I get one example for you. I cannot really remember what's actually the linear relationship or this quadratic relationship of those two lines, but from here, what I want to say is this green line is the upper bound of this red line. Why? Because, remember, I get a magic say. For the upper bound, I get a magic say. And you may say, okay, right now it seems all the values actually n is smaller than 100. This blue line is under this red line. But remember, I can explain, because I don't care about small n values, I care big ones. As long as from the bigger ones, this green line is above this red line, that's the upper bound. Now we get it? I can explain from another way. I get a magic number for say. You said, okay, this one right now is here. I will increase the value for say. So upper bound is a theoretical concept. It's only to say, okay, we tend to understand some very big problems. So for the big problems, normally you get a very big input space. So that will be n. So what we care is when n is large, we get a one function. It's always theoretically above the running time of the current algorithm. Excuse me. From where we call that one is upper bound. Okay, now we get the, from here, let me check it. Okay, now I think you deserve 10 minutes of the break, and then we'll get back to talking about the bounds. Thank you. Okay, guys. Can you settle down, please? Okay, thank you. So let's carry on. So now, remember what we get is we talked about the running time of the algorithms. It's actually determined by the basic operations and the running time of that basic operations. And the Cn is the number of the time you run the basic operations. And then we go to the concept to say we want to compare two algorithms. But the difficulty is different algorithms get different running time complexities. So in that case, how do we compare? So we got some ideas like we need to use the bounds. So we talked about one bound like the upper bound. And you may think, okay, now it seems you get more than one bound. Correct. So we get upper bound, we get lower bound, we get exact bound. Don't worry, we'll talk that one by one. So now that's the whole story. And right now what we get is we go to that point. So after we're talking about bounds, we want to use the bounds to actually group those algorithms, the running time, into something we call equivalent class, and then compare from there. Now we get the idea. So possibly you know this one already, something called a big O, the big O notation. So the big O actually here is given for the upper bound. So we get O. So that's the informal definition for the upper bound. So that's actually O, Gn. Remember, Gn is the function. It's the upper bound function. And O is actually called, that's we call, big O is actually mean that's the upper bound. And that's the formal definition as I mentioned before. So we get a magic C. So as long as we get a C is positive, and multiply the upper bound function Gn, and you always keep the Cgn is actually above the line of the current running time Tn, and we call that one is upper bound, especially considering for n is large. So that is the upper bound. And now let's get some examples. So we get here is actually I get Tn, remember Tn is the running time, and running time for this example is equal to 5.1 n. I hope you still remember that straight line, that linear line, straight line. So that's Tn equal to 5.1 n. And here we get the upper bound is something like that, Gn, 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 three options. Now, I get explanation for each one of them. For example, something like this. If we just get Gn equal to n, and you may think right now, okay, it seems actually the coefficient for this Gn is 1 is less than for 5.1. So it seems this one is not actually above the line for Tn equal to 5.1 n. But don't forget we get a magic C. So the magic C is as long as the C is positive, so the C actually is invisible here, but the C can be large. So it can be larger than 5.1. So it is upper bound. Now we check the second one. We get a point 0.001 and minus 6. And in this case, we get a coefficient is very small, but don't forget we get a magic C. So that means the coefficient you get from here does not matter. Correct. That's it. And then we check Gn equal to n squared. So because right now we get n is actually to the power of 1, and here you get n squared. So this one is the quadratic, so this one is above this one. So that's what we show within that example. So all these one are actually the upper bound. Okay, now we get something like this. So what Gn to use if Tn equal to 5.2 n? So which of the upper bound function like this one should we use? Correct. Yeah, because as we said, the coefficient here actually does not matter. So as long as actually you get n equal to this n to the power of 1, or you get higher, and then you get this one can be the upper bound. That's correct. No, so any of the above should be possible.
What if the coefficient is 6,000.001?
Okay, in that case, does not matter. Because what we care here actually is we say, okay, you get an invisible magic C. That C can be large. And even you get this C is millions, you get this coefficient is millions, but as long as I get an invisible one, that can be millions and millions. So it is larger. And for n, it can be even larger. So in this case, what are we talking? We do not talk a specific value. So when we say n is large, I did not say n is large because n is a million of something. I just say n is large. So when we say n is large, it is large tend to be infinity or something. So that's the one we're talking. So we're talking in theory. So that's the one. Yeah. So now we continue. So now, within the previous slides, we said, okay, we get for one of those, for one of the running time function, we get multiple upper bounds. But how can we do that? So the thing is actually we need to use some of those common equivalence classes. And here we get a list of them. And one is actually the one you mentioned about linear ones. So we get different ones. So we can, in fact, group all of them into a small number of this. But how to do that, we will show in the following slides. This slide is telling you, okay, now you get different upper bounds. We can group them into equivalent classes. So what are those equivalent classes? That's all of them, not all. That's the one we covered within here. So some examples. So let me explain. So the first one is actually what we call constant. So like access array element. And the second one is a logarithmic. It's actually something like the binary search. And for what actually is a binary search, don't worry, we will cover in the following weeks. So for all the examples, if you can understand, that's great. If you hear about it, that's great. If you never hear about that, don't worry. That's the one we will cover in the following weeks. But the point here, actually, you get a constant, log, linear, arithmetic, and you get a quadratic, exponential, factorial. You get a different equivalent classes. And all of them is actually used to describe the trend of the running time. This one is even more clear. So now let's look at this graph. The x-axis is still n. Now let's start n from 1 and increase this one to 1,000. It's not that large, but it's at least larger than 1. So we increase n like this. If we look at the red line, it's actually constant. So as long as you increase n, does not change. Does not change the trend for this constant function. But then you go to upper one, you will see the green one, sorry, the blue one is actually log. So you get a log trend like this. You get a linear, you get a linearistic, and you get a quadratic, exponential, you get a factorial. And for each of them, the point is, each of these equivalent class describe one way of the growing trend for the running algorithms. So that is the point. In another way, each one of them is enough to distinguish itself from the rest. So that's what we call group all those running times into different equivalent classes. Now, let me be more specific. So if we're talking about those linear ones, if we're talking about those linear ones, what we mean is the linear one, as we show you the example, you get a two linear function, 5.1n, 5.2n. What we try to distinguish is we distinguish whether this one is linear or it is nonlinear, quadratic, factorial. We don't care if it is linear, what is the coefficient? We don't care about the coefficient here. So what we mean is we group 5.1n and 5.2n into a group called equivalent class linear. That's the story. Now, as long as you get this one, perfect. Now we continue. So now let's recall something. So we want to find the equivalent function class that upper bound different Tn. Because different algorithms get different Tn's. We want to find one of the equivalent class actually can upper bound all of that. So what we do here actually, we want to do something like this. So if we get one of the running time for algorithm 1, algorithm 2, algorithm 3, you get a different running time functions. Can we simplify them and run them and write them in a different way to be one of those equivalent classes? Yes, we can. That's what we're going to do. So we do something like that. So we do that by doing the following guidelines. Something like this. So as I mentioned, okay, you said, you can said, within the previous example, you said the coefficient does not matter, the constant in there does not matter. So the simple will be, okay, we just admit them. So we discard them, we don't care. So the first rule is we do not include the constant. So we get 0.01 and minus 6. Minus 6 actually is the constant. So we just omit it, we do not use it, we don't care. We'll remove negative 6 here, and we'll omit all the lower order terms for something like this. We got 3 terms, n cubed, n square, and n. And from here we can see within the 3 terms, the one dominant is actually the highest order of n. So we simplify by remove the last 2. So that's it. That's what we do. The second rule. And then the third one is, as we mentioned, okay, the coefficient seems does not matter, even for the highest order. So in that case, we just omit it. So 3 ways will help you to simplify the current running function for a specific algorithm and make it equal to one of the equivalent class. After you've done that, you can compare between different different algorithms. Now, we see the beauty of this one. So we do all of the different steps, calculation, the final we say, we get something called equivalent class, and we can compare A and B. So that's the one we do those calculations. Okay, now, if we're using all these rules, and we do with the previous upper bound, as example we showed you before, like 0.1 and minus 6, and ON, and all of them actually will be equal to this function. That's the linear function. So it will be ON, because we omit this constant, and we omit this coefficient, and also we get ON for this function, and this ON is just ON itself. So these two are actually equivalent to each other. So that's the way we compare the different running time functions from different algorithms. That's the whole story. Now, any questions about this? Okay, now we continue. Okay, now I get one question for you. So we get one Gn function. Remember, Gn actually is the upper bound. So it's upper bound for the running times of one algorithm. So if we use the previous guideline, as in the previous slides, can you just work out the equivalent class for this one? And again, we get this form, and you can just scan by this QR code. So please fill in that one and select the right answer there. Okay, we got 27 right now, 28. So please do it. Okay, now let's look at the responses. Okay, the majority get it right. That actually is the ON. Sorry, I cannot use the within the Google form. We cannot use it. I have to use ON up square 4. So that's one I can get. So which means that's ON to the power of 4. Yeah. So this one is the correct answer. So the reason is, for example, within the question. Let me bring the question. So within this question, as we said before, we first remove this one. We remove actually 50 because that's constant. and for all the for this lower order of those n's, and we get the highest order is equal to 4. So we can just ignore all the 43 n3 minus n. So we get 2n4 left. And then we again omit all those coefficients. So we get n4. So the right answer is n4. So now let's get back. You will say, okay, most of you get it right. So if you still have questions, go through the recordings and attend the tutorials, because in the tutorials in this week is actually for running next week. So the tutorial 2 will cover the mathematics we talked today with more exercises. So please make sure you attend. Okay, now, after we talk about the upper bound, we got something like the lower bound. So lower bound is something like that. It's the opposite of the upper bound. So again, we got one function. And here we got omega. And omega function is something like this. But before I go through the mathematical definition, let's look at this graph. I like the graph because this one is much easier for us to grab the concept. So it's something like that. So Tn is the running time. So the line Tn is showing the running time for one algorithm, and the Cgn actually is the lower bound. It means actually as long as Tn go to large numbers, the Cgn is always under this line. So we call Cgn here is the lower bound. So again, we use a different term. Previously we use O, big O, and here we use omega. We use omega. So Dn here will be the lower bound. And again, we say C actually is a magic positive number. And we do that for large n. If n is small, we really do not care. So it does not matter if n is small. So that's the lower bound. And then we get another function called exact bound. Something like you get upper bound, lower bound, you get something in the middle. In the middle one is a bit special because this one get 2 lines. The 2 lines with 2 magic numbers, C1 and C2. So the mathematical way will be something like this. The Gn is one of the functions with 2 parameters, C1 and C2. Both of them are actually larger than 1 are positive numbers. And as long as they use different C1 and C2 and they keep C1 Gn is above Tn, and C2 Gn is always lower than Tn, and we call the Cgn actually here is the exact bound. So as long as you get a concept like this, that's fine. So I will not ask you to analyze the exact bound for one of the specific algorithm. So that's the exact bound. You know upper bound, lower bound, you get exact bound. And for exact bound, we get a different notation. If you know this one is the theta. If you don't know, just remember this one, the theta. Theta is for exact bound, omega is actually for lower bound, and you get a big O is for upper bound. You get 3 bounds. Any question up to now? Yeah, so we continue. Here I give you one of the tables. The table shows something like that. And here, within this column, we get different running time functions, log 2n and 10n plus 5, different running time, Tn. And here, this one is the big O, so that is upper bound. Upper bound, different upper bound, on square, and on cube. And this one is omega, which means that actually is the lower bound. So it's the lower bound actually get 3. And here the T and F means that the true or false. So this one basically means log 2n. The question is On the upper bound of log 2n? The answer is true. So I will not go through everything here for this example, but I hope you can go through after the lecture for each one of them. Make sure you understand. If you can go through this one all correctly, come to me. I'll give you 1 chocolate. Sorry, I'm kidding. What I try to emphasize something like that. So as long as you can understand the concept within lecture, great. But you do need to test whether you can do that individually after the class. It's a different story. So I suggest you do this one after the lecture tonight if you have time, maybe tomorrow. Go through all of them, make sure you understand. Any questions? go back to watch the recording again to make sure you understand. If you still cannot get it, find me next Monday in my office. Or you post something online, we can discuss there. So that's all the questions. And now we got, so we got something we need to clarify. Something like that. So we get the upper bound, lower bound, exact bound, but make sure you do not mix them with the worst case efficiency, best case efficiency, or average case efficiency. They are not the same. But in some cases, it is reasonable. You can use the upper bound or lower bound to describe the worst case efficiency or the best case efficiency. Sometimes you can use it, but please make sure they are two different things. So I will not try to justify what actually the difference is between them. I just want to make sure you understand those two are different things. Do not mix them together. For the relationship of those two, don't worry. It's actually beyond this course. It's some mathematical concept. So we don't care, as long as we know they are different. Okay, now we get something like this. Why we get different bounds? Because sometimes we get the upper bound is actually most commonly used. But the exact bound can tell us something. You will never get something actually you do not expect. So an exact bound can actually tell you how that algorithm can run. That is the tightest bound you can give for one of the running algorithms. This something like upper bound is something you can always bound what actually the running time for the count algorithm. The lower bound is something like if your algorithm grew to some order with cases, you cannot actually get a better performance than your lower bound. That is the lower bound. So the exact bound is actually in the middle. Try to get the tightest description of that running times. And the lower bound actually sometimes will be used to describe how fast your algorithm can be. So that's the way of different bounds. It's just a mathematical concept. It's a bit abstract, but I hope you can understand to the level we discussed. That's what we need for this course. And then we need to analyze two algorithms, recursive and non-recursive. So we go from the non-recursive first. So in case you don't know actually what actually is the recursive one, the recursive is something you give one function and you call itself and recursively. And when we actually do not consider something like that, we give one problem. The first thing you get is you possibly will get a pseudocode of it. You will not get a running time like estimation of the running time for that algorithm. Normally, that's the job you need to do. So normally, you get a pseudocode of it, and you need to work out what actually is the running time theoretically based on the pseudocode in papers. So that's what we did. So from here, actually, we want to use it. And we do two kind of algorithm analysis, the recursive and non-recursive. But for either one of them, we do two steps. We first estimate the running time, and then we determine a bound and order of growth. Now we get something like, we get a bound, we get an order of growth. It's actually constant, linear, log, quadratic, factorial, exponential. That is the order of the growth. That is the order of growth we call equivalent classes. So now we continue to analyze this non-recursive algorithm using what we have just covered. Okay, now we get the first one. So within the non-recursive one, what we do is we first need to identify what actually is the input size, what is the basic operation, and then we determine the number of basic operation executions. So remember, to get the running time for one algorithm, we need three things. You need to know what actually is the basic operation, and you need to know how many times that basic operation are executed, and then you need to understand, okay, for the running time for each of the operations. And that one actually is determined, that one plus multiply the number of times you run the basic operation, you will get a running time. But don't forget, Cn, the number of runtime of the basic operation for one algorithm is actually based on the input space. So we need to find input space, basic operation, work out the number of basic operations for that algorithm by doing two steps. we set up a summation for say n to reflecting the algorithm of the loop structure, and then we simplify this summation. That's what we do. Now we get our old friend. We get equivalent class, and then we use the equivalent class Gn to describe what is the running time for we analysis in the previous steps, and we get a bound from there. Okay, now we get a recursive example. So that's non-recursive one. So we get n to the power of n. So our old friend, and here again. So we use it to analyze. So something like that. We know the size. The input size actually is n. We know the basic operation here we call is a multiply. And what is the Cn? Cn is the number of times we run it. Okay, now we get input space is n. And can you tell me what is Cn? How did you get it? Who can explain? Raise your hand, please.
You only perform multiplication once per each n. Like for each iteration, sorry.
That's what we did, right? Yeah. So basically what we did is for each I, we get 1, run 1 plus 1 plus 1 plus 1. So we set up one summation to go through this. Great. So I'll give you one chocolate. Cool. Now, we get this one. So this summation is important. But sometimes I'm lazy. I don't want to go through plus 1 for 1 million times. That only taking 30 years to do that. So I want to get something like this. I get a very nice math notation to say I get sigma as a summation 1 for multiple times, n times. And how do we determine the times you go? By using two parameters, I and n. I actually is the initial start status. We start from 1 and stop at n, so which means we run n times. So a big relief. So I don't just spend 30 years to run all those 1 plus 1 for 1 million. So basically what we did here is actually, we try to set up one of the summation function to calculate, and then we need to simplify this one. Okay, now we go another example. Here we get a for loop statement. It's nested. So the question here is we get two matrices, A and B, and I actually want to add them together. So the basic way is actually we go through each of the elements in those two matrices and add them together. So that's something like 4i across the first A, and then 4j across the second dimension, and then we get aij plus bij and go to cij. So we do the addition like this. Okay, now we get some questions. So can you tell me what is the input size? Raise your hand, please. Say it again. Okay, that's one good try. Okay, so the answer is actually n, but I would get one chocolate to the one who tried for n square. Who get n square? Raise your hand, please. I will try. Sorry if I did not get you. Yeah. Okay, now let me go back to recall what actually input size. So n square is a good try. N square actually you are talking how many loops, iterations you need to go through. But what here I want to talk is the input size. The input size actually is for the problem. So the problem for this addition about those two metrics is actually n. So it is n. So the basic operation here actually is what we found in the middle, addition. And then can you tell me what is the say n? Who get it? Yeah. So n squared, can you explain?
So the n will be running twice, first 4 times in the outer loop and the 4 times in the inner loop. Yes. So it will be running twice. That's why.
Okay, great. Raise your hand, please. Let me find where you are. Sorry. Yeah. Thank you for your help. Now we get this one. So Here is we get two summations. Now, let me explain. I will steal two words from you, the inner and outer, the inner-outer loops. So we get two summations. This one is actually the inner summation. The inner summation actually is for the inner loop. And the outer one is actually for the outer loop, is for the outer summation. We do one is actually for one calculation of this addition. So now we do that is for say n. That is the number of times we run the basic operation within this algorithm. Any question in here?
What about if they have both of dimensions n by n? What's the input size? N by n.
You mean n by n is the size of the matrix?
Yeah.
Now here what do we get is n by n matrix.
What about n by n?
So it's still n.
Still n?
Yes. Because here the matrix we discussed is n by n. It is n by n. Yeah. Now, so we get this one. Now we get the Cn. And then now we get question? Sorry? Say it again. Okay, you mean get a square matrix? If you get a square matrix, there'll be something different. But remember, if you know how actually computer implement your square matrix, sometimes they just do that in a linear way, so that will be a different story. But if you say, okay, I'll give you a square matrix like n by n, which means you just replace n right now to n squared. In that case, it is different. It is n squared. Any more questions? Cool. Now we continue. Okay, now after we get the summation, we want to simplify them. So how do we do that? So we simplify, we get some of those rules. So let me go through each one of them. For those rules, don't worry. How to get the rules is not our job. Because it's the guy actually who coded mathematics who gave out those rules. And even what we can get is we can get it from the appendix within the textbook. So what we do is you remember what are they and use it to simplify the running function the running time function for one algorithm. That's fine. So now let's go through each one of them. So we get different kind of use for series, like for the summation. If this summation actually is from I equal to L to N, and we can simplify this one to here. And for here, we don't know how to do it, but if we go here, I think we know how to do it, right? We just use some of the rules to omit all those constants, omit those low rank those n's, and then we omit all those coefficients, so we get the final equivalent classes. And after we do the simplification like this, we will be able to simplify this impression again to those equivalent classes. That's what we do. By using different rules, and if you get this one, if this one is constant, you get a sum. If you get this one is I is the variable, you try to sum, that's the sum index I, and then you call this one geometric, so you get different ways to replace it, and you get distributive, and you get associative. Associative, actually, you can separate A and B, and for distributive, actually, you get C, and you can bring C to the front of the sum. So that's the different ways. Now, let's see how do we use it. We get our old friend again. So A to the power of n. So remember we get a Cn equal to this. The summation, that's your story, right? Yeah. So we get the summation of Cn equal to the sum of 1 from I equal to L, I equal to 1 to n, and with some n times. So we will do something like this. So that's the running time for the A to the power of n algorithm. And we first use rule 1 to replace it. We get n minus 1 plus 1. So finally we get n. So now you may find, okay, Cn equal to n, it actually leads us to the equivalent class. We can use, okay, now the algorithm for A to the power of n, we get the running time finally equal to Cn equal to n. For the equivalent class, it's actually equal to big O n, because we only get n left. And now let's do another one. This one is a little bit complicated because you get inner and outer summation. And now let's do it again. So what we do here actually is we use the rule 1 to replace the inner one. So that will be n minus 1 plus 1. So we simplify, we get n in the inner. And right now we say, okay, this summation is summation for n summation for n from 0 to n minus 1. In this time, n here is actually a constant. So we can bring this one to the front of the summation. And then finally, what we get is n here, and sum this one, we will use rule 1 again to get n minus 1 plus 1. So we get n, so we get n squared. So now for the second one, to calculate the addition of a and b to c, and what we get actually, the equivalent class here is Cn equal to n squared. So that is the way we do the calculation. Any question about this one? Okay, cool. So now we do analyze the recursive algorithms. So for recursive algorithms, actually what we do this one is we find one of the functions, we'll call it itself again and again to solve some problems. But don't forget, as long as you do the recursive one, you still get one condition to stop. That one is what we call the termination condition. You always need to get one like that. So if we want to do algorithms like this, analyze them, so the point here is we need to go through some of those recursion steps. Now let's look at one example. Let's look at this example to calculate the factorial. So we get fn, basically the factorial means you fn, n is the input, you n multiply n minus 1, n minus 2 until you get multiply 3 to 1. So that's factorial n. Excuse me. So we get fn. So here actually is the algorithm. Here is the pseudocode. So we get 5 steps. We get if n equal to 1, we return 1. Please pay attention to here. The stop condition here, the return 1, here actually it just return. There's no something we call the basic operation here. And here, if it's not, we return something like fn minus 1 multiply n, so we get a multiply here. So the point here is we need to determine the input size and the basic operation within that recursive factorial calculation. And then we find the recurrence relationship for Cn, not for Fn. Fn is the factor of n, and this Cn is the count of the number of running times for n, when the input space is n. So now we try to find this recursive relationship, and finally we simplify the recurrence relationship using the methods within Appendix B. I will show you later how to do that. And finally, we determine the equivalent classes. Okay, now we try to find the recurrence relationship present in the sequence of the terms in the original problem, like the calculation of the factorial. So what we do here actually is we get a sequence of a factorial of n is actually fn to something like this. But it can be presented like this. So what actually is this recurrence relationship mean is something like this. We got fn equal to fn minus 1 multiply n. So that's the recurrence. That's the recurrence relationship between f function. What we try to get is we try to get the recursive relationship within the Cn function from here. And then the stop condition is f1 equal to 1, but the c1 does not equal to 1. Because the c1 means you go to 1, you just return something. You don't need to execute the basic operation like multiply. Now, let's make it clear. So we try to find a recurrence relationship for Cn. So what I mean here actually is for the basic operations, and we can find the basic operations actually is you do the recursive every iteration, you will do the calculation for multiply, right? So the basic operation here actually is multiply. The input size here actually is n because you get n is actually the input. So that's input size. And now the recursive relationship and the condition is something like this. Cn equal to Cn minus 1 plus 1, and for n larger than 1 and say 1 equal to 0. So, okay, now one question. Can you tell me why C1 equal to 0? C1 do not equal to 1?
Because when n is 1, it's not doing any multiplications, it's returning 1.
Correct. Can you raise your hand? Cool, I will try. Sorry. Okay, now that's correct. Because when we count for Cn, Cn is counted for the number of the basic operation executions. When n equal to 1, you just return 1. There's no multiply operation, so you don't need to do. So which means C1 equal to 0. But when Cn and Cn minus 1, the relationship is coming from here. So Cn to Cn minus 1 actually is do one more multiply operation. So here what you get is actually Cn the count plus 1. So that is actually the recurrence relationship for Cn in recursive algorithm analysis. And after you get this idea, then we can start to the simplification. So simplification will be something like this. So we try to aim to simplify this one as we found. So what we do is we start with the recurrence relationship Cn equal to Cn minus 1 plus something for Cn minus 1 or something. So what we do is we substitute the Cn1 with its RHS. It's short term actually is for what actually you can get Cn minus 1 by using recursive iterations. And you do these steps one by one to replace Cn minus 2, and do one by one, and until finally you spot some patterns, the Cn and introduce a variable to express this pattern. So this pattern really means something like that. So determine when the value of this variable that relate is Cn equal to C1 plus something. So what is the something? It's actually, let's try get from here. So we get the recurrence relationship is actually Cn minus 1 plus 1 for n larger than 1, and C1 equal to 0. So we first do Cn equal to Cn minus 1 plus 1, and then we substitute Cn minus 1 equal to Cn minus 2 plus 1. So we get something like this. So in the previous slides, what we did, we do that in description. And from here, we try to put within those equations. So they are actually the same slides in different way to talk. So now we replace Cn minus 1 to the right side of this equation. And we continue to do that for Cn minus 2. We get the right side replaced within here. So we get something like this. From here, what you can get actually is when we actually substitute Cn minus 2 with the expression in terms of Cn minus 3, you get the term 1 more here. So you will increase this one by 1. So we get 2, now we get 3. So that is the pattern for the calculation of those basic operations within recursive algorithm. We carry on, and we see the pattern is Cn equal to Cn minus 1 plus I emerges. This I is actually from 1, 2, 3, and it goes through. And finally, we replace C1 equal 0. So what we get final value is something like this. So Cn is actually equal to n minus 1, because when n equal to 1, we return 0. We did not return 1. So that means, okay, you get n minus 1. But when we're talking about these things like this, what we do is we do the simplification of the running time, Tn, in terms of Cn for this factorial algorithm. But when we're actually talking about the bounds, we will remove this -1 constant. So that will be n. That is, we get Tn equal to Cn plus n. We get On is the upper bound. Okay, now we get the final slides for today. what we talked within this subset is we talked about how do we do the analysis for non-recursive and recursive algorithms by using the input size, basic space, the number of times we run the basic operation, and finally we get the running time algorithm, so running time function, Tn, and then we simplify. I hope you can review everything we talked today after the lecture to get a better, clear idea. Okay, cool. Thank you, everyone. Yeah, thank you.
Yeah, if we're going to meet up on.
Yep. Yep. Can I get it?
Yeah,
Okay.
I had to calculate the end of regular
So which part do you understand?
the formula of that recursive cost. Yeah,
This one?
this one.
Okay.
How do you
So
get
it's something like that. So let's go back to previous slides to see what actually is the recursive relation between the calculation for Cn. So that's Cn.
Yeah.
So Cn is different from f. C actually count, the function count the number of execution for basic operations, and the factorial is actually to the calculation. So this one means, so the fn equal to fn minus 1 multiply n, you can understand, right? If you want to get fn, you need to call fn minus 1 then plus n. Yeah. And then from here, that will be okay. If you want to get the number of counts for the execution of the basic operations for n, we need to get the operations for n minus 1 first, plus 1. This one is this calculation, this multiply calculation.
Oh, I get it.
Yeah, so that's Cn equal to Cn minus 1 plus 1. And
yeah.
when you go back to the end, to n equal to 1 C1, and there's no multiply, there's just return 1.
Yeah,
So
I
C1 equal to
So
0.
actually, it's execute twice because it should
Yeah.
calculate what is n minus 1, then
Yeah.
it should macro this too.
Yes. So this one is the calculation for factorial. This one is the calculation of the number of execution for that basic operation. So the relation here is actually multiply. Here will be addition. Yeah, that's the difference.
Yeah, I have another question.
Yeah,
It's
sure.
about the average case.
Yeah,
Sorry.
that one I know is pretty abstract.
Yeah, because yeah, I wonder about the p, the probability of sorry, where's yeah, the probability, the p.
Yeah.
Yeah, this one. So it's a probability of successful search. Then, is there any other value of p besides 1 and 0?
No.
So
Because
just 1 and 0. 1
no. Sorry, I got you.
Yeah.
So p can be the one from 0 to 1. Any value in the middle is possible.
Okay.
So I did not say that because I don't want to make them even more confusing.
Okay.
So these are those two extreme cases. P either equal to 1, either equal to 0. So that's what we discussed, the extreme case. So clearly P can be 0.1, 0.2, point something. So even we go there, you need to use this one to calculate the average case running time.
So 0 means it's impossible
Yeah.
to get